Okay, let's try again. Tariffs and economic motives. Now, as you all know, in all engineering projects, with the exception of the construction of works of art, the question of cost is the first importance. In fact, most cases, the cost decides whether a project will be undertaken or not, although political and other considerations may intervene. However, the design and construction of an electric power system is undertaken for the purpose of producing electric power to be sold at a profit. Hence, every effort is made to produce power as cheaply as possible. So the problem of calculating the cost of any scheme is often difficult because the cost varies considerably with time, tariffs, and even with convention. In general, the cost of producing electric power can be roughly divided into the following two portions. A, fixed cost. And these do not vary with the operation of the plant. It means these are independent of the number of units of electricity produced, and it mainly consists of interest on capital investment, allowance for depreciation, i.e. wearing out of depreciable parts of the plant, the transmission and distribution systems. Then two, all right, that I've said, taxes and insurance, most of the salaries and wages, and a small portion of fuel cost. Then we get to the running cost or the operating cost. These vary with the operation of the plant. These are proportional to the number of units of electric energy generated, and are mostly made up of the following: most of the fuel cost, a small portion of salaries and wages, repair and maintenance. Then, as we go to maintenance, depreciation. It is obvious that from the day of the construction of a generating plant, is completed, deterioration starts, and due to wear and tear from the use and the age of physical decay from lapse of time, the results is a reduction in the value of the plant, a loss of some part of the capital investment in the perishable property. The rate of wear and disintegration depends on conditions under which the plant apparatus is working, how it's protected from the elements, and how promptly the required repairs are carried out. Okay, the useful life of the apparatus ends when its repair becomes so frequent and expensive that it's found cheaper to retire the equipment and replace it by a new one. All right, so they've got some important methods of providing for depreciation: straight line method, diminishing value method, retirement expense method, and the sinking fund method. Now these are too old and cumbersome, so we are just going to look at the straight line method and the sinking fund method. Okay, in the sinking fund method, provision is made for setting aside each year sum as invested at a certain interest compounded annually will equal the amount of depreciable property at the end of its useful life. As compared to straight line method, it requires smaller amounts, and also the amounts of annuity are uniform. Okay, and that brings us to the formula. Q is equal to small q 1 plus r to the power of n minus 1, or Q is big Q r divided by 1 plus r divided by 1 plus r to the power of n minus 1. So the total annual charge on the installation is RP plus Q. That means the plant should bring in so much money in a year. Okay, let's look at a problem or two. Well, first, let me get this again. Yeah. Come on. Why doesn't new share want to work? Gee, what's going on now? Oh, come on. Okay. Is it better like this, or can you see? We must determine the annual charge on an installation costing 500,000 Rand. To buy and install, the estimated life being 30 years and negligible scrap value. The interest is 4% compound annually. Now, since the scrap value is negligible, we can say that Q is equal to P. And therefore, Q is 500,000, R, which is the interest rate, is 0.04, and the number of years is 30. So if we substitute it in there, Q is then 500,000 times 0.04 divided by 1,04, divided by 1,04 to the power of 30 minus 1. That gives you 8,572 Rand and 60 cents. So the total cost on installation per annum will be RP plus Q, which is 0.04 times 500,000 plus the interest and depreciation value. So that means we're going to pay in 28,572 Rand per annum. So that by 30 years we can replace this equipment. Then a power plant having an initial cost of 250,000 has an estimated scrap value of 30,000 at the end of its useful life of 20 years. Determine the annual deposit necessary if it's calculated by the straight line method and the sinking fund method. So the scrap 1 Q is equal to P minus the scrap value, which is small q. So that's 250,000 minus 30,000 gives us 220,000. And then our interest rate is 7% and 20 years. So the total depreciation after 20 years will be that whole amount with the sinking fund method. So the total depreciation per annum will then the total amount divided by the number of years, that gives us 11,000. So the annual deposit will be RP plus Q, which is 0.07 times 250,000 plus 11,000 comes to 28,500. Now, if we use the sinking fund method, Q is Q times R plus R divided by R1 divided by 1 plus interest times to the power of 20 minus 1 gives us a value of 5,015 Rand and 37 cents. So the annual deposit will be 0.07, which is R times P, which is 250,000 plus 5,015, that gives us 18,015 Rand annually. So if we deposit that, we will be able to buy new equipment at the end of 20 years. So a plant initially costing 500,000 Rand has an estimated salvage value of 100,000 at the end of 20 years. What will the valuation be halfway through its life? Through the straight line method and the sinking method with an 8% interest compound. So the total depreciation is 500,000 minus 100,000, that gives us 400,000. So the depreciation in 10 years, that will be half-life. So that's 400,000 divided by 2 means it's 200,000. So the value after 10 years will be 500,000 minus 200,000, which gives us 300,000. If we use the sinking fund method, we get 400,000 times 0.08 divided by 1,08 divided by 1.08 to the power of 20 minus 1. That gives us 8,093 and 40 cents. So at the end of 10 years, it will be 8,093 times 1,08 divided by 0.8. You now see it's the opposite of what we are calculating normally. Times 1,08 times 10 to the power of 10 minus 1. That gives us a value of 126,625. So at the end of 10 years, it will be 500,000 minus 126,625. That gives us 373 Rand and 375 cents. 373,375. Okay. If we now go back to the desktop, if I can find it again. Well, actually, I have to have two computers to do this. Oh. Right, the next thing that you are going to look at is factors influencing the cost and tariffs of electric supply. So the first one is demand. By demand of a system, it's meant the load required, usually in kilowatt or kVA, averaged over a suitable and specified interval of time of short duration. It should be noted that the demand means the load average over an interval of time. There is no such thing as an instantaneous demand. Then we talk about average demand. Average demand of an installation is meant its average power required during some specified period of time of considerable duration, such as a day, a month, or a year, give us daily, monthly, or yearly average power respectively. So in this way, we get the arithmetic average, which is the kilowatt consumed in the period, divided by the hours in the period. Maximum demand of an installation is defined as the greatest of all the demands which have occurred during a given period. It is measured according to specifications over a prescribed time interval during a certain period, such as a day, month, or a year. It should be clearly understood that this is not the greatest instantaneous demand, but the greatest average power demand occurring any of the relatively short intervals of 1 minute, 15 minutes, or 30 minutes duration of that period. Now you will see with this thing, even if your maximum demand for that 1 minute is over a certain period, you are going to pay for that whole period the biggest amount of that one that you've created. So that's why we have maximum demand control, so that whenever we reach a certain maximum, the machines are switched off, which are not necessary for the production. Maybe air cons or fans or something like that. And there's a graph, maximum demand determinations, mostly used for estimating the capacity and hence the cost of the generator and electrical apparatus required for the servicing a certain specific load. Well, you can go and read all of this. Let's look at the demand factor. It is defined as the ratio of the actual maximum demand made by the load to the rating of the connected load. So the demand factor is equal to the maximum demand divided by the connected load. Okay. Then we've got an example. Suppose a residence has the following connected load: 3 60-watt lamps, 10 40-watt lamps, 4 100-watt lamps, and 5 10-watt lamps. Assume that the demand meter indicates a 30-minute maximum demand of 650 watt. We must determine the demand factor. So the connected load is 3 times 60 plus 10 times 40 plus 4 times 100 plus 5 times 10, which is 1,030 watts. The 30-minute maximum demand was 650 watt. So the demand factor was 650 divided by 1,030, which is more or less 63%. So they say the demand factors of lighting installations are usually fairly constant because lighting loads are not subject to such sudden and pronounced variation like power tools. Now the diversity factor is called the maximum demand over the connected load. These are all formulas that you should know by heart because we're going to use them all of the time now. Load factor, defined as the ratio of the average power to the maximum demand. Right, it is necessary that in each case the time interval over the maximum demand is based and the period over which the power is averaged must be definitely specified. If, for example, the maximum demand is based on a 30-minute interval and the power is averaged over a month, then it's known as a half-hour monthly load factor. And load factors are usually expressed as percentages. So when applied to a generating station, the annual load factor is the number of units actually supplied per year divided by the maximum number of units that can be supplied. So there we have the definitions. Annual load factor, monthly load factor. Okay. Okay, the significance of the load factor is in fact an index to the proportion of the whole time a generator plant or system is being worked to its full capacity. The generating equipment has to be selected on the basis of a maximum power demand that is likely to be imposed on it. However, because of general nature of things, it seldom happens that a generating equipment is imposed on it during all the time, 8,760 hours of a year. But whether the equipment is being worked to its full capacity or not, there are certain fixed charges like interest, depreciation, taxes, insurance, part of salaries, which are adding up continuously. In other words, the equipment is costing money to its owner, whether it's working or idle. So it earns a net profit only during those hours when it's fully loaded, and the more it is fully loaded, the more is the profit to the owner. So he wants a good load factor. So let's look at another example. The consumer has the following connected load: 10 lamps of 60 watt each and 2 heaters of 1000 watt each. The maximum demand is 1500 watt. On average, he uses 8 lamps for 5 hours a day and each heater for 3 hours a day. Find the total load, monthly energy consumption, and the load factor. So the total connected load will be 10 times 60 plus 2 times 1000, which is 2000 watt. Now the daily energy consumption was this 8 times 60 for 5 hours plus 2 times 1000 for 3 hours, which gives us 8,400 watt hours. So the monthly consumption will be 8,400 times 30, which is 252 kilowatt hours. And the monthly load factor is then 252 divided by 1,500. Now he's converted everything to kilowatts. That's why it's 10 minus 3 times 24 times 30. That gives us 23.3%. Okay, and then example 5. The load survey of a small town gives the following categories of expected loads. Residential lighting, 1000 kilowatt, duty factor of 60%, and a group duty factor of 3. Commercial lighting, 300 kilowatt, duty factor 75, group factor 1.5. Street lighting 50, percentage DF 100, and group DF 1. Domestic power, 300 kilowatt, 50% and 1.5. Industrial power, 1,800, 55% and 1.2. What should be the kVA capacity of the substation, assuming a station power factor of 0.8 lagging? So, for residential lighting, the total maximum demand is 1,000 times 0.6, which is 600 kilowatt. Maximum demand of the group is 600 divided by 3, which is the demand factor. That gives us 200 kilowatt. Commercial lighting is total maximum demand is 300 times 0.75, which is 225 kilowatts. And the maximum demand of the group is again 225 divided by 1.5. It's 150 kilowatt. Street lighting, 50 kilowatt. Demand of the group will then 50 divided by 1 is 50 kilowatt. So the total domestic power is 300 times 0.5, which is 150 kilowatt. And the maximum demand of the group is 150 divided by 1.5, which is 100 kilowatt. So you see there's the demand factor and the group demand factor. So the industrial power will be the total maximum demand, 1,800 times 0.55, which gives us 990 kilowatt. So the maximum demand of the group will be 990 divided by 1.25, 1.2, that gives us 825 kilowatt. So the total maximum demand on the station will be 200 plus 150 plus 50 plus 100 plus 825. So that's 1,325 kilowatt. Capacity of the substation required at a power factor of 0.8 lagging will be 1325 divided by 0.8. That gives us 1656 kVA. Okay, then we'll do just another example for tonight. A consumer has the following load schedule for a day. From midnight to 6 a.m., 200 watt. From 6 a.m. to 12 noon, 3 kilowatt. From 12 noon to 1 p.m., 100 watt. 1 p.m. to 4 p.m., 4,000 watt. And then from 4 to 9, 2,000 watt. And 9 to midnight, 1,000 watt. What is the load factor? And if the tariff is 50 cents per kilowatt of maximum demand, plus 35 cents per kilowatt hour, find the daily bill. So the energy consumed during the day is 200 times 6, plus 3,000 for 6 hours again, plus 100 for 1 hour, plus 4,000 for 3 hours, and 2,000 watt for 5 hours, and 1,000 watt for 3 hours. That gives us 44,300 watt hours. So the average power, that will be 44,300 divided by 24, which gives us 1846 watts. So the daily load factor is the average power over the maximum demand, which is 1846 divided by 4,000. Where did I give that again? And the maximum demand was 4,000. So that gives us 0.461%. So since the maximum demand is 4 kilowatt, the maximum demand charge is 4 times half. That gives us 2 rand, whatever it is, 2 rand. And then energy consumed is 44.3 kilowatt hour, and the energy charge is 44.3 times 35 over 100. That gives us 15 rand 50. So the daily bill for the consumer is 2 rand plus 15.50, which is 17 rand 50. So here we can see that the maximum demand during any period was 4,000 watt. So that's the maximum power demand. So the tariff is 50 cents per kilowatt hour. So we've got $0.50, okay, 4 kilowatt. Maximum demand charge is 4 times 50 cents, which gives us 2 rand. And also that's 35 cents per kilowatt hour is then 44.3 times 0.35 cents. Okay, any questions so far? Right, then we'll call it a night. and we'll go on next week. Have a good weekend and enjoy your studies. Good night.